All right, so let's see what we got for Unit 4. Unit 4's test seems like I think I said is going to be a little bit shorter. You won't have any options, though, for the short answers, but there's going to be fewer multiple choice and fewer vocabulary just because we didn't cover as much material. So the test is still a little bit vague, but what I did was I have the review sheet in front of me that I gave you, and I kind of pulled slides. So one of the things we talked about with regard to our Milky Way galaxy is it was kind of controversial, is whether our galaxy was a galaxy or not. Instead of a galaxy, the option was maybe that when we look at something like the Andromeda, we're not looking at the Andromeda galaxy, we're just looking at the Andromeda nebula. So that's what kind of the controversy is. Is it like an island universe of stars that would be a galaxy, or is it just simply kind of a nebulous object within our own galaxy? And of course, this one was right. When we look at something called the Andromeda, it's not the Andromeda nebula, it's the Andromeda galaxy. So something like that. And then the other thing related to that whole concept of a galaxy, there was this thing called the Shapley-Curtis debate. And actually, it was Shapley that said that that those things like Andromeda was just a nebula, not its own galaxy. And it was Curtis that actually said that those things we're looking at, like Andromeda, was its own galaxy, just like the Milky Way galaxy. But that debate was in 1920, and they didn't really decide anything until, dun, 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 they used a tool. I'm kind of looking at my notes here. They used a tool that was actually developed in 1912. So it's 1920 for the debate. 1912, Henrietta Leavitt, a woman astrophysicist, I would imagine, actually was looking at these sort of a type of star that is moving on the HR diagram. It's left the main sequence, and its brightness is varying. It's called a variable star. So Cepheid variables actually can be used to ultimately get to distance, basically, and actually I'm going to talk about that more in a later part in Unit 4. But the distance to this Andromeda object actually said that it's not the Andromeda nebula, it's an Andromeda galaxy. Because then it was the next slide, I believe, Edwin Hubble used Henrietta Leavitt's technique and came up with that Andromeda nebula is actually Andromeda galaxy, because it's located very much outside of our galaxy, 2.2 million light years away. Our galaxy is only about 100,000 light years in diameter. So this is kind of this May 9th, 4th, 9th, and 31st is kind of showing you how that Cepheid variable is kind of pulsating. I think that is so cool. So Cepheid variables can be used to find distance, and that's how we knew that the concept of a galaxy versus just kind of our universe is the Milky Way galaxy. So there are other galaxies, things we kind of take for granted. Let's see. 2.2 million light years. William Herschel determined the center of our galaxy. So, yep, Herschel. Oh man, you're gonna have to insert a slide. So before this, there's a slide about William Herschel, and William Herschel actually said, well, we can find the center of our galaxy, the Milky Way galaxy, if we kind of look for kind of where the light is kind of centered or concentrated, and it didn't it didn't work, because he came up with the center of our galaxy is around our sun, or around our Earth even, and the problem was that some of the light got diminished, and he couldn't really get a good sense of where stuff was concentrated. Otherwise, he would have been onto something. So Herschel didn't do it right. Then actually, globular clusters are one of my favorite sort of objects to look at through the nighttime sky. Here's a globular cluster. Actually, then Shapley used the fact that kind of globular clusters buzz around that supermassive black hole in the center of our galaxy. So globular clusters are kind of, we're going to see it here in a minute, around in the halo region, around what we call our nuclear bulge. And the nuclear bulge is the center of our galaxy. Let's see what else we got. How do we map our own galaxy? We look to other galaxies for clues. So this is actually Messier Object 83, a galaxy, and you can see it's a barred spiral galaxy, kind of like ours, barred spiral, and it gives us a sense for what our galaxy might look like. And again, I talked in class where this is a face-on view versus an edge-on view, and this is so this is in visible light, and this is looking at it in radio waves. And of course, to me, it looks like there's a lot more going on here than there is here, and that's because we're looking actually at dust and clouds of material that can birth new stars at this particular wavelength. I think that's pretty cool. All right. What type of galaxy is the Milky Way? Well, the Milky Way is a barred spiral. Let's see if I barred spiral. Barred. It's not a regular spiral. It's a barred spiral galaxy. And you can kind of see the bar of stars here and a major arms extending from there. Speaking of major arms, this isn't a figure, but it's kind of words so much. We are on a short arm called the Orion arm, and actually then the long arms on either side of us are Sagittarius and Perseus, and that's confirmed right here. Here we are, Orion. Here is, oh, it looks like Perseus, and they're calling this Carina. What else do I have? Maybe that might be about it. So in general, oh, yeah, I like this one. This actually gives some dimensions here. So kind of generally know, this is what our Milky Way we think would look like face on, and this is what it would look like edge on. And I mentioned those kind of, that Shapley looked at those globular clusters. These dots here are globular clusters of stars, and they kind of help us to find the center of our galaxy. The center of our galaxy is a supermassive black hole. We'll be talking about that, called Sagittarius A star. So the distance between the center of our galaxy and us is about 26,000 light years, and then this distance is about 100,000 light years. 100,000 LY light years. All right, so that would be the anatomy and distances of our galaxies. Sagittarius, of course, is a constellation, and Sagittarius A star is actually the center of our galaxy. And I know maybe it was Reed that was like, well, how come it's so bright there? Well, but how can be a black hole and be bright? Well, that brightness, actually that radiation, this might be taken in infrared, but that radiation is on what we say this side of what we call the event horizon. So that radiation can escape, but if it would have been any closer to the black hole, it wouldn't have escaped. So Sagittarius A star is the center of our galaxy. Speaking of then, well, I guess not speaking of, hold that thought, Sagittarius A star. This is actually looking at, I think, another galaxy, a galaxy called NGC 4144, but and it's showing you the path that the stars take around the center, so the center of the galaxy. And these are disk stars. Disk stars, you can kind of see the red is showing you the disk stars. They're nice and orderly, orbiting the center of the galaxy. And then we have these halo stars that are kind of wild children. So they have different orbital patterns, but all stars need to orbit or fall into the center of their galaxy. Let's see, orbit patterns. Oops, sorry, go back. Next one. So this is looking at, this is the center of a galaxy. I don't know, our galaxy could be the Milky Way galaxy. And going farther away from the center, this is showing, these are stars that are farther away from the center. And this is showing how fast they move. So actually this curve, the red curve, is what it actually does. And what it actually does is this up here. Now this bit up here is what we say the deviation from what we expect. So the blue line is what we expect. So that going up like that, in kind of how fast stars move if they get out to the edge of our galaxy, that is weird. And the reason it does that actually has to do with the presence of dark matter. So if you go ahead and, I think there might be a picture coming up, but if you go ahead and take our Milky Way galaxy and in what we call the halo region, outside the plane of the Milky Way galaxy, that's the halo, If you go ahead and put a bunch of dark matter, then you can explain why stars out in the edge orbit faster than they should. Okay, so what is dark matter? Well, dark matter might be just normal stuff, but it might be something more exotic. Let's see, our sun's orbit about the center of our galaxy. I have one slide on that. I just think that's pretty cool. So our sun, along with the other stars, are kind of just orbiting this Sagittarius, what we call Sagittarius A star, at a safe distance from the supermassive black hole. And the fact that it goes this fast actually means that it has made one trip, our star, since it was born. Let's see, based on, oh no, it's made more than one trip, sorry, because it's more than this old. It takes 230 million years to complete one trip around the galaxy. So last time it was where it is, actually, it was the early age of the dinosaurs. So that'll be a question kind of related to that somehow. This busy looking figure actually is showing you Sagittarius A star. I'm not sure, it must be here, kind of where all those, kind of the middle of the chaos. And each little kind of circle here is showing you the path of a star. So what they did to understand that we had a black hole in the middle of our galaxy is to basically take, to watch how these stars orbit Sagittarius A star, and that gave the mass of the object. And then they could go ahead and kind of do, they could go ahead and get the volume just by, you know, just the volume, the area of it. And they could then understand how much mass must be packed in that small area, and then that's where they got some sort of critical density that they know that that is actually a black hole. All right, 4 main types of galaxies. So there's Edwin Hubble. So 4 main types of galaxies. We have regular spirals, barred spirals, that's us, ellipticals, and irregulars. And they can be arranged on what we call a two-fork diagram that Edwin Hubble came up with. All right. So here are the E for ellipticals, S for spirals, and SB for barred spirals. And then I wanted to mention, and I think my sheet here says that there are subtle differences. So I don't know if you can see them here, but I'm going to focus on the spirals first. Actually, the way this works is if you have, I'll put loose winding, okay? Actually, that's going to give you a thin bulge, okay? And we're going to call that spiral C. Now, spiral A actually means that it's tightly wound arms, and it will give you a thick bulge. Okay, so it just does. So these are kind of subcategories of spirals. We have a analogous in barred spirals. These aren't regular spirals. These are barred spirals called SBs. So we'll start over here. An SBA, actually you're going to be tightly wound, and you're going to have a thick bulge. And if I compare that to the barred spiral C, you're going to have thin wound, and you are actually going to have a thin bulge. All right, something like that. Ellipticals, I don't know, I don't think there's a question like this, but you can see where your E0s are really spherical, and then as they get more kind of drawn out, you increase the number. So E7s are more drawn out than E0s are most circular. So, oh, excuse me. All right. On to the next. All right, so as far as a galaxy goes, any galaxy, whether this is a spiral galaxy, excuse me, but any galaxy, well, ellipticals don't really have a disk, but the spirals and the barred spirals have a disk region. They have a halo region outside the galaxy. This is showing you spiral arms. There's a bulge in the center. I guess these are mostly terms associated with spiral galaxies. All right. Then we go on to the next part where we're taking these galaxies and we're organizing them. So the first thing that galaxies are going to be organized in is something called a cluster. And remember, I talked in class where there is gravity going on. So these lights here are not stars. These lights are actually galaxies. So the cluster that the Milky Way belongs to is called the local group. Okay. All right. Yeah. And then I'm looking at my notes. It looks like on my notes I've got something, yeah, right here in this order. Oh, I'll go right here. This is actually just showing you more the local group, the group of clusters that the Milky Way belongs to. The group of clusters, sorry, that the cluster of the local group is the cluster of galaxies that the Milky Way belongs to. Final answer. So clusters of galaxies I have in my notes here can be rich or poor, and rich or poor just depends on how many galaxies they have. So poor galaxies have, poor clusters have few galaxies. Rich clusters have large numbers of galaxies. Yeah, what else do I have? Superclusters. Next. Okay, so so galaxies are held together in clusters, and well, this is actually looking at rich and poor. No, there we go. This one will work. The galaxy clusters, like the local group, then is grouped into things called superclusters. And guess what? We are in the local supercluster. But I actually watched a video where we're actually in something even more cooler name than that, aren't we? Let's see. This says that actually within the supercluster, the clusters of galaxies are not gravitationally stuck to each other. And then the other thing I have for this chapter is the fact that, and I'll show you here, sponge. So keep that in mind. Sponge has these void areas, and like in the universe, there are these void areas where there are no galaxies. And so it kind of looks like this, where this is mapping the universe as we see it. And these dots, again, do not mean stars. These dots are actually galaxies. So I don't know if you can kind of get a sense for kind of some void regions where there are no galaxies, galaxy clusters. All right, on to the next one. So galaxies can interact, and it looks like I've picked two types of interactions, and I've got slides here to show you. They interact, and depending upon the relative sizes, we can call them mergers. So this would be an example of, you can almost look like two galaxies here merging, and we've been talking that the Milky Way and Andromeda galaxy have similar sizes, and they are actually going to merge to form one galaxy, humongous galaxy one of these days. The other type of galaxy is cannibalism. So you can't tell it right here. This looks like just one kind of irregular galaxy, and as it turns out, if you look close, you'll see it has two hearts. This is its two hearts. So this would be the small one, and it was cannibalized by the large one. And these are just an indication of what the hearts, the you know what I mean, the supermassive black holes in the center of those galaxies before they merged. They are kept intact at this point, but I do think they're probably going to merge at some point. But this is showing you kind of what went on behind the scenes. All right. Okay, cosmology. Oh, man. Looks like, well, hopefully you might want to find this slide. The only thing I was going to show you here was cosmology, and cosmology is actually just kind of the layout of the universe. Think of it that way. So that's pretty cool. Oh, yes, there was more here. Then the other thing, when you find the slide, it's going to tell you that we can actually use these things called bulbs. Let's see, standard candles. STD for standard candles. Sometimes called standard bulbs. Standard candle bulbs. And so what that means is, and I tried to kind of show this in class where, and you know this to be true, like if you have, if you're looking at a car and the car's lights are really bright, okay, then the car is close to you. If you take that same car and you look at them and they're kind of dim, you're like, well, they must be farther from me. And so you are already kind of saying, well, I know kind of how normally bright they are, and I'm using how bright they appear to get to distance. That's exactly what we use in astronomy. So in order for that to work, we kind of have to know what the standard, what it really should appear like. So this part was all about kind of getting to distances, because in order to understand the layout of the universe, you need to kind of be able to get to distances. So this is an HR diagram of two clusters of stars, the Hyades and the Pleiades. And so what they're doing here is comparing this star with this star, because they are similar, they should have similar brightnesses. But if we go over here, we can see that this one is this bright. We go over here, that this is apparent brightness, not absolute magnitude. So, but this one is brighter because it is closer. And actually, this is called sequence fitting. We can actually kind of use this to our advantage. All right. What else? Well, this one was actually, we already talked about this. The Cepheid variable star, the one that leaves the main sequence as it's aging and kind of starts to change in its luminosity. This is what Henrietta Leavitt came up with, and that what Edwin Hubble used to find the distance to the Milky Way galaxy. And so this is actually showing you how this works. Each of these dots represents a Cepheid variable star. And depending upon how long it takes for it to pulse, to kind of get brighter and dimmer, that's actually related to how much energy it's pumping out, its luminosity. Then if we compare how bright we know it really is, how much energy it's really putting out, if we compare that to how bright it appears, we can get to distance. That's using Cepheid variables as a standard candle. And then this actually, of the standard candles I've talked about, this standard candle gets the farthest away. And I kind of apologized in class because we didn't get to this topic, but we talked about a nova event dealing with a bloated red giant dumping on a white dwarf. Well, this is actually where the white dwarf gets overloaded from its companion star, and it blows up. And it's called a supernova. Unfortunately, I wish they would have come up with a different term, because we already have a supernova. This is a special supernova called Type 1A. So bottom line is that what you're looking at here, I like this. This is the before and the after, before and the after, and the before and the after. The little afters here, the little bright dot, actually is the energy of a supernova event. And they're very standard in that they only have certain conditions that they blow up to, so they always have a certain amount of brightness to them. And so again, we just compare how bright it really is and come up with distance. So does this make sense that this one would be the furthest away because it's the dimmest, and this one would be the closest because it's the brightest, because these all have the same amount of energy pumping out. All right, what else do I have? Expanding universe. So Hubble then was gathering data on galaxies, now that we knew them to be galaxies, not just kind of like nebula within our own galaxy. And what he found out about those galaxies was that they had an apparent redshift. And we've talked about the Doppler effect, the Doppler redshift before. Red means something's moving away from you. And so as it turns out, these galaxies are all moving away from us. Okay, we call that recessional motion. And the next figure I'm going to show shows you kind of, well, here it is. So the universe is expanding. The galaxies are all, well, pretty much. We said we're on a collision course with the Andromeda, so how can that work? Well, throw that one out. But most galaxies are moving away from us. And basically, you're going to see it a minute plotted, but the further away the galaxy is, the faster it's moving away from us or receding. So this actually was Hubble's data. And so I know it's a little scattered, but can you see where the further it is from us, the faster it's moving? Okay, and then this was his original data, and then this was more data. And you can kind of see where, yeah, I think there's a straight line there. And as it turns out, let's see, Hubble's law, Hubble's constant. I wonder if I have. No. I wouldn't worry about Hubble's constant. Well, I don't know. That straight line, actually, we can go ahead and get an equation. I can't think of what the equation is right off the top of my head. But we can get an equation that shows, that shows Hubble's flow, these galaxies moving away from us. I'm kind of drawing a blank, so. The last slide I have for that chapter is this one, where this is actually getting farther and farther away. So we can actually use radar within our solar system to get to distances. We can use the phenomenon of parallax. Remember, where a star, as the Earth orbits the sun, 6 months later, we see the star move against the background stars right here. And to get to relatively nearby stars, we can use that main sequence fitting to remember where we had two clusters of stars plot on an HR diagram and kind of compare the brightnesses of the ones we know that need to have common brightnesses. To get a little farther, we can use Cepheid variable stars in distant galaxies to get to their distance. And we can use white dwarf supernovas as standard candles. And then actually we can use how fast the recessional velocity of a galaxy and Hubble's constant, that's h0. Well, maybe this will work. h0 to get to distance. Is that it? No, one more. Okay, so one last topic we talked about, and again, I was a little apologetic because we didn't get to kind of Einstein's relativity, but I think we saw a video that I liked about this. But so at the heart of gravitational lensing is that we need to have a lot of matter. And remember, we talked about how galaxies are organized in clusters, and those galaxies are actually gravitationally bound. Think of them being kind of like in a glue of dark matter. We said the Milky Way has dark matter in its halo region. Kind of all galaxies have dark matter in their halo region. Now, what's up with that dark matter? Well, that dark matter then actually can create this phenomenon we call gravitational lensing. Any matter can create gravitational lensing. And it's kind of hard to show you here, but what we're showing here is this galaxy is creating a dent in what we call the fabric of space and time. And it's causing the light from this distant quasar to be bent. So here this comes the light being bent. Okay, being bent. And so actually this quasar looks like it's right here, and it's coming here, it's being bent, and it's actually the quasar looks like it's here. So you actually get in that video watch called like Einstein's cross, where you have kind of 4 images. From a single image you end up with kind of 4, but there's just 2 shown here. So gravitational lensing is great in that it can allow us to see further, just like our lenses allow us to see further. So what you're looking at here is actually, this is a galaxy that's creating a dent in the fabric of space and time, and you can kind of see some, well, you can see it better here. This is the image of a distant object that light is being gravitationally lensed by that galaxy. So I think that's it.